Assalamu alaikum class. Today we are going to start our chapter number 9, and the title of the chapter is Combinational Circuit Design. Basically, the digital logic is divided into combination and the sequential circuits. Combinational circuits are those whose outputs depend only on the present input, while the sequential circuits have some memory. So generally we can say that the building block for the combination circuits are the logic gates, while the building block for the sequential circuits are the registers and the latches. So this chapter focuses on the combinational logic, and the next chapter, chapter 10, examines the sequential logics. So in this chapter we introduce the CMOS logic with the assumption that the MOS transistors act as a very simple switch. The static CMOS gates use complementary NMOS and the PMOS networks to drive the 0 or the 1 output respectively. And in this chapter we examine the techniques to optimize the combinational circuits for lower delay or energy. The vast majority of the circuits use the static CMOS because it is robust, fast, energy efficient and easy to design. However, there are some certain circuits have particularly uh, power or density restrictions that force another solution. So such alternatives CMOS logic configurations are called the circuit families. So the main target in this chapter is the circuit family. In the introduction we are going to discuss some different types of the optimization technique. So firstly we have input ordering delay effect. The logical effort and the parasitic delay of different gate inputs are often different. Some logical gates like the AO121 in the previous sections are inherently asymmetric, that one input sees less capacitance than the other. So other gates like the NAND nodes are non-nominally symmetric but actually have slightly different logical effort and the parasitic delays for the different inputs. So here we are going to calculate the parasitic delay for the output, and this circuit is basically the circuitry of the NAND gate in which we are going to find out the delay estimation. So firstly we consider the following output transitions when it occur and both the inputs held a stable 1 and the other rises from 0. We consider the value of both the inputs are 1 and other rises from 0 through the NMOS transistor to the input A. The Elmore delay is basically 7 RC, and therefore if the input arrival time is known, then we can find out the least input to the inner terminal. So there are two different kind of the scenarios when we are going to find out the, as I have already told you about that some logical gates like the AO121 is basically asymmetric because in that one input sees less capacitance than the another. So if we apply to the asymmetric gates, and we are going to discuss about what are the delays and the value of the delay in particularly asymmetric gates and how we can find out. So when one input is basically far less critical than another, even nominally symmetric gates can be made asymmetric to favor the late input at the expense of the early one. So in a series network, this involves connecting the early input to the output transistor and making the transistor wider so that it offers less series resistance when the critical input arrives. So in case of the parallel, that you can see that here the early input is connected to a narrow transistor to reduce the parasitic capacitance. So in this example, which is the example of a NAND gate, we can see that under the ordinary conditions, the path acts as a buffer between A and Y. You can see from here. So when the reset is exerted to the path forces the output low. If reset only occur under the exceptional circumstances and can take place slowly, the circuit should be optimized for input to output delay at the expense of the rest. This can be done with the asymmetric NAND gate that is already given into this. The pull down resistance is basically R by 4, and the gate still offers the same driver as a unit inverter. However, the capacitance on the input A is only 10 by 3. So the logical effort is 10 by 9. This is better than 4 by 3, which is nominally associated with the NAND gate. This can be very clear. So in the case of the asymmetric gate approach is equal to 1 on the critical input, but the total logical effort goes up. So CMOS transistors are usually velocity saturated, and thus the series transistors carry more current than the long channel model would predict. The next is basically the next circuit is basically our skewed gate. What are the skewed gate? In all other cases, one input transition is more important than the other. So if you remember in the chapter 2, we discuss about the high skewed gates to favor the rising output transition and the low skewed gate to favor the falling output transition. So this favor can be done decreasing the size of the non-critical transistors. The logical efforts of the rising up or falling down transitions are called GU and GD respectively, and are the ratio of the input capacitance of the skewed gate to the input capacitance of the unskewed inverter with equal drive for the transition. So it's a high skewed inverter, it's an unskewed inverter, and it's the unskewed inverter equal to rise resistance, and it's the unskewed inverter, and it's the unskewed inverter equal you can easily calculate the logical effect by comparing to unskewed inverter with the same effective resistance on that edge. So GU, that I have already told you, the logical effort for the rising up is basically 2.5 divided by 3 is equal to 5.6, and GD, which is the logical effort for falling down, is basically the same as 5 by 6. The degree of the sequeing, the ratio of the effective resistance for the fast transition relative to the slow transition impacts the logical efforts, and noise margin, a factor of the two, is common between us. Let's have the revision of the high and the low skewed logical efforts of the skewed gate for a particular transition is the ratio of the input capacitance of that gate to the input capacitance of the unskewed inverter, deriving the same output current for the same transition. And again we are revising high skew and the low skew. High skew favoring the rising output, and the low skew is favoring the falling output, and the logical effort is smaller for favor the directions but the larger for the other direction. And so here is the basically catalog of the circuit gates, in which you can see that the unsecured inverter, NAND and NOR gate, and high secured and the low secured inverter, NAND 2 and NOT good 2. So we are going to calculating the logical effort rising and logical effort falling of from this catalog, and then finally we will get the logical efforts of all the three main NOR basic gates of CMOS technology. The next circuitry is about the PN ratio. So if you remember or recall the catalog of the circuit gate, then we can notice that the average logical effort of the low secure NOR 2 is actually better than that of the unsecured gate, and that is a very different thing that we can observe here. So the PMOS transistor in the unsecured gate are enormous in order to provide equal rise delay. The contribution input capacitance for both the transitions while only helping the rising delay. By accepting a slower rise delay, the PMOS transistor can be downsized to reduce the input capacitance and average delay significantly. So in general, what is the best PN ratio for the logical gate? We can say that the ratio of the PMOS and the NMOS transition width. You can prove this all, and then next section that what is the best PN ratio. Let's have a very brief example of PN ratio in terms of the inverter, NAND or NOR 2. So the fastest PN ratio you can observe from here. This is your lecture problem. You are supposed to annotate your designs with the transistor size that achieve this relay. Each input and can represent the maximum of the 16 lambda of the transistor. So in case of any question you have, you can easily ask from me. So this is all for the today's session. Thank you. Allah Hafiz.